We are going to be studying, let me find my book, we are going to be studying rotational circular motion. So let's first kind of get an idea of the difference between rotational and circular motion. Circular motion is literally what it says. You're moving in a circle. So if you think of this stopper that's on the end of the string here, if I twirl that stopper and hopefully not hit anybody, that stopper is moving in circular motion. So what is rotational motion? Any ideas?
Whenever you have something turning, something around, and stuff spinning.
That's it. If I have the object that is turning around or rotating, it is undergoing rotational motion then. Now, if there's a fly sitting on this rotating object, then that fly is undergoing circular motion. But the fly itself is not rotating. Unless it was sitting right on the center, then it would also be rotating with the object. You're right. It would if it was in that position. So when we have something that is undergoing circular motion, that has a speed that is called tangential speed to it. Now, what is tangent? What does that word mean? Not in trig function definition and geometry definition. What does tangent mean?
Something that's touching, like whenever you have like a circle and a line.
If I have a circle and I have a line coming by, and if it just touches the circle at one point, it would be a tangent line. Josh?
I was going to say that it's perpendicular to the radius and the same distance from the center of the circle as the radius is length.
A tangent line would also be perpendicular to the radius of the circle that is tangent with. Absolutely. Those are some of the geometry things we learned about tangent lines. So let's see if you can guess on what will happen. If, and I won't do it right now because I'll probably hit something, but this is the imagination thing that we are going to do for just a moment. If I am spinning this in a horizontal circle, and if I let this stopper go, or I let go of the string, when that stopper came around and was exactly right in front of me. So I'm looking right here at the wall, the corner of the wall by that TV. If I let it go now, where would that stopper go?
If you let it go, wouldn't it just be farther out and then like?
Would it, so here's my question, would it travel towards the blackboard? Would it travel straight down the room? Would it travel towards Christian right over there? What would it do?
If you let go right when it was right in
If I
front of you,
let it go when it's right in front of me, I'm staring right there at that.
it's going to hit the, no,
thing,
it's
right?
going to go straight to your left.
That way
Yeah,
to the
so I
board.
think it's going to hit. It's going to go straight to the left without hitting anything back to the back of the room.
Yeah. I think it would just fall down. I feel like if you applied force in the direction, it would go that way. But like if you just let it go.
Well, gravity certainly will pull it down, but it will move forward in some forward direction for a little while. So that's kind of the question. In what forward direction will it
Yeah,
go?
perfect reaction time, and you did it directly in front of you, it's going to hit the back of the pipe.
Are you questioning that I don't have perfect reaction time?
Yes.
No.
All right. Some of you may need to hold your hands up for protection. So let's see if I can do it here. Let it go at exactly the right time.
The board, that was the board.
I did a real good job of letting it go exactly at the right time. How does it go?
You guys
It goes the way that it's swinging.
It goes tangent to that circle, exactly perpendicular, thank you, David, exactly perpendicular to the radius. It did not travel out towards the board. It did not continue around a little more and hit Christian over there. So I knew if I was reasonably good, you guys were safe, because I was spinning it over here, and so it should go like that. And right here, this is what happens to it. It is going to go exactly tangent to the circle when I let go of that. So we'll study a few reasons of why it's going to go exactly like that. What do we know from Newton's first law? Do you remember that? Remember what Newton's first law was about?
Object is at rest.
Object at rest stays at rest. Object in motion
Force is in place.
keeps moving how?
Unless it's just going by motion or something.
Keeps moving, David.
At the same rate.
Unless there's something.
Okay, well, you've all said that. Keeps moving in a straight line.
Oh.
Keep moving in a straight line unless some other force acts on it. Now, the only force acting on it once I let it go was gravity, which is why I pulled it down, and we all knew that would happen.
And wind resistance on the string.
And there is a little wind resistance to it, but minimal enough that we can ignore that part. So it will continue straight in a line. As we are coming around at any point in time, let me pick this instant in time. At that instant in time, the direction that the bob is going is really tangent to it. Right there, at any instant in time, that's the direction it is moving. And this is called its tangential speed, or tangential velocity. How fast it's moving. That's our tangential velocity. The tangential speed of an object in circular motion is the object's speed along an imaginary line drawn tangent to the circular path. Now, tangential speed depends on the distance from the object to the center of the circular path. If I keep my hand rotating at the same rate up here, what will happen if I shorten the radius to how fast that bob is moving?
It's going to go faster.
It's going to go faster. Is exactly right. It's going to go faster. And a little hard for me to let it out, but it goes slower if I let it out. When the tangential speed is constant, the motion is described as uniform circular motion. Now, the only time, according to Newton's first law, that an object changes direction is if there is some force acting on it. Otherwise, it will just continue in a straight line. So you tell me which direction is the force acting on this bob right now as I'm spinning it, so that it doesn't just continue going in a straight line, but it curves and goes in a circle.
It's your hand pulling on the string.
Josh, what did you say?
Your hand pulling the string to pull it towards you.
That is the only force, now ignore gravity, that is the only force acting on it. Do you believe that I cannot push this thing forward with my string? I hope you believe that. I can't. Do you believe I cannot push like this with the string and provide any force? I can't. I can do none of this. I can do none of this. The only thing I can do is pull. That's all I can do. The only force I can apply to this is pulling it towards the center. So that is the reason it is going to go in a circle. And when we have things that are directed towards the center of a circle, we call it center-directed or centripetal. And the meaning of that word is center-directed. So let's see if I can't grab this thing where we can see it in the video as well as get it small enough to actually manipulate it a little bit.
You wrote them.
All right.
Wait, so centrifugal and centripetal, those are two different words?
Those are two different words. Centrifugal with an F is a different word than centripetal with a P. That is correct.
One of those and no one told me anything?
Yeah, those are two very distinctly different things.
A car moving in a circular path experiences acceleration even when the speed at which it is traveling remains constant. This is because acceleration depends on velocity, and velocity is a vector with both magnitude and direction. When the car moves in a circle, the direction of the velocity vector is constantly changing. Therefore, the acceleration, or change in velocity over the change in time, is also changing. Acceleration of this nature is called a centripetal, or center-seeking acceleration. When the radius decreases, the direction changes more quickly and the experienced acceleration is greater. When the radius increases, the direction changes more gradually and the experienced acceleration is not as noticeable.
So you've experienced that. If you were in a car and you were going at 50 miles an hour and you have this big sweeping turn, there's not much force acting on you trying to pull you towards the center of that. But if you, what's that? And we're even going to talk about that. Yeah, what's happening to us that we're trying to fall out the door when we're turning. We'll talk about that too. But there's not a lot of force when it's a big sweeping turn, right? But if you're still going at 50 miles an hour and you have this really sharp 90-degree turn, well, if your car makes the corner, there would be a lot of force acting on you in order for you to make that corner. Why is it again that when I'm moving at a constant tangential velocity in a circle, we still call that accelerating? Because changing direction. Correct. Velocity is a vector quantity including direction. So when I change direction, I am accelerating simply by doing that, by changing direction.
I tell my parents that, and then they say that that's why I have bad grade in physics, is because I don't understand.
It's true. It's right. Just changing direction is accelerating. So let's look here at centripetal acceleration. The acceleration of an object moving in a circular path at a constant speed is due to the change in direction. So it's accelerating simply by changing direction. An acceleration of this nature called centripetal acceleration, and here's our first formula for the new chapter. Centripetal acceleration, A sub c, is tangential speed squared divided by the radius of that circular path. First problem, 226, number 4. Let's see if we can make it work. A race car moving along a circular track has a centripetal acceleration of 15.4 meters per second squared. So they just indicated to us what the centripetal acceleration was. If the car has a tangential speed of 30 meters per second, what is the distance between the car and the center of the track? Well, as soon as you know this formula, it's a real simple problem. All we have to do is solve for that r. So if I multiply by r, I then have to divide by the a. So r would equal tangential speed squared divided by our centripetal acceleration. And we've got our working formula. Nice and straightforward. So what was it? 30, which we'll have to square. And our acceleration was 15.4. And if you want to run a calculator for me, how big a circle is it?
58.4.
58.4. And what unit are we talking about?
Meters.
Meters. The distance that we just have. All right, so the first concept is centripetal acceleration takes place because we're changing direction. I can be moving at a constant speed, but if I'm going in a circle, I'm changing direction, therefore I'm accelerating, and this is the formula that will tell me how fast I am accelerating. Centripetal acceleration, how do we know it's directed toward the center? Well, this little diagram can help us understand. Hopefully the string also helps you understand. The only way I can apply force is towards the center. So we're going to accelerate the direction of that net force towards the center. But let's look at this diagram. At point A, my tangent is that v sub I. That's my initial velocity. Then as we move around the circle to point B, I have a final velocity in that direction. By definition, acceleration is change in velocity over change in time. And we know change in velocity is going to be final velocity minus initial velocity over change in time. And if I am drawing with vectors, a negative of a vector means the opposite direction of the vector. So right over here, I've made a little purple vector that is simply the opposite direction, same size as that initial vector. So I have a negative v sub I. So I'm just going to put end to end the v sub f and the negative v sub I vector. And if I put them end to end, guess where the change is? Right there. If I go final minus initial, which is just the opposite direction of it. So beginning to end, right there is my change in velocity. And that green arrow is pointed right at the center of that circle. So there's a vector representation of those things. Down here in part B, they did it, the v sub f minus the v sub I, but they didn't orient it exactly as up there.
Yeah, that's what I was about to ask. So you'd have to consider that the angle would be 90 right there. You could say that because it doesn't look like it's 90 down there.
Which angle is 90?
Between your green vector and the v sub f, yeah.
That is 90.
So
correct. That picture down there.
Okay.
Whoever the graphic artist didn't understand the physics when they drew the picture. So, see, even when you become a graphical artist, you need to know physics. All right. Centripetal acceleration is always directed toward the center of that circle. Second kind of acceleration is tangential acceleration. So what we've seen first is the centripetal acceleration directed toward the center simply from changing direction. Tangential acceleration now involves a change of speed of how fast something is moving in a circle. So just like the tangential speed or velocity is how fast it's moving linear, so many meters per second. It has a tangential speed at any point in time. Well, I have a tangential acceleration if I increase my rotation like that. Then I accelerated it. Or if I slow it down, of course, that's a change in tangential velocity. So it also is an acceleration. So we can have a tangential acceleration as well as a centripetal acceleration. You can keep those two straight. To understand the difference between centripetal and tangential acceleration, consider a car traveling on a circular path. They're kind of going to repeat what we've already said. Because the car is moving in a circle, the car has centripetal component of acceleration towards the center. It has this. It's accelerating towards the center. If the car's speed changes, now this car happens to be moving, it's moving in a clockwise direction, I guess. If the car speed changes, the car also has a tangential component of acceleration. So they drew their arrow right here. They actually did this one first. So we have a car that is accelerating linearly, tangential, and turning a corner, centripetal. So if we wanted to know the total acceleration of that car, we would need to combine these two. Graphically, they have drawn it right over here. From beginning to end, that is going to be my total acceleration of what this car is doing. It is also towards the center of it. And the total acceleration then would be, this is a right triangle, because when I'm tangent, I'm perpendicular to the radius, and I could just use right triangle trigonometry, Pythagorean theorem, and get what it was, and I could get the angle to it as well. So let's talk a little bit about, did I go backwards? I went backwards. Let's talk a little bit about centripetal force. Now, that force that is pulling me so that I turn a corner. Consider a ball of mass m that's being whirled in a horizontal circular path of radius r with some constant speed. The force exerted by the string has a horizontal component and a vertical component to it. When I am twirling this, I can't twirl it exactly horizontally. If you were up at the level with it, you would see it's dropping just a little bit because gravity's pulling it down. So the only way I can twirl it is at an angle a little bit like this. The only way I can twirl it, here we are at an angle. My hand is up there at the end of that arrow. So I could resolve it into its components that are 90 degrees to each other, right here and here. This part is working against gravity. That keeps it from falling down. And this part down here is going to be the force that causes it to go in a circle. It will also be the net force because gravity will just cancel out this vertical one. And so the only thing left over will be this. So that's what they're saying when they say we have a horizontal component and we have a vertical component. Vertical is counteracting gravity. Question?
So whatever you get for the force of gravity will always be the upper component, will it be the same?
Correct. Force of gravity would be exactly equal to this vertical component right here, because that's the only thing I'm battling against is gravity that's trying to pull it down. So my vertical component will be exactly equal to it, if I'm keeping it at a steady pace going around. So this net force or centripetal force is this one right over here. And here is the formula to get centripetal force. But we really already knew this formula if we thought about Newton's second law, rearranged a little bit. Force equals mass times acceleration. So if we already know, hey, here is centripetal acceleration, then all I need to do is multiply mass times the centripetal acceleration, and I will have the centripetal force. So here's the centripetal force formula all broken down. It's just mass times centripetal acceleration. V squared over R. So, well, yeah, it uses some of the same things we've seen in others.
So you're just adding mass to that? And that's
All we're doing is multiplying mass by that centripetal acceleration that we had before. So it's just m times this previous formula.
So-
M times that previous formula.
So if you're trying to find mass, could you
Try mass,
multiply the acceleration?
multiply by R, divide by the velocity squared, tangential velocity squared. Yeah, we could rearrange it. Let's talk about this car that we were going around this circle in for a moment. Let me see if that is my... Yeah, I'll go here. We'll put it right there. Oops, that had a problem on it. I'll just have to do it at the bottom. Let's talk about the car. So here goes the road. Turning this corner. Dash line. Here you are in your blue car. Overhead view. So there's the blue car. There's the top of your blue car. That's a Ferrari, yes. So there you are. You are turning this corner. You're turning this corner like that. What is the thing that is providing the centripetal force, the force towards the center, so that you actually turn that corner like the green thing is? There's no string. The wheels, friction with the road. That's providing the force. So that car's wheels are setting on the road. The only way I'm going to have a force toward the center, now obviously I turn my wheel, but the thing that provides my force is going to be the friction. Otherwise, I'm just going to keep on going what direction? Straight. In fact, that's what you are doing as a passenger. You are not experiencing a force that's pushing you out the door of the car. You are simply obeying Newton's first law, which says you're going to continue straight unless a force acts on you. In reality, the car is turning underneath you. You're trying to go straight. Now, if the car is turning underneath you and you're trying to go straight, well, you will slide to the outside. It will feel like there's some force pulling you out. There's not. If the door is open, it's not that you're sliding out, it's that the car is leaving you suspended in the same spot. And so it turns away, you go out the door because the car has left you, and you keep going straight. So if you don't have your seatbelt on, which you're all going to wear, but if you don't have your seatbelt on, then you slide over to the door over there, and then the door is pushing on you a centripetal force, a center-directed force.
Is that why, like, when you're riding a motorcycle, they have to, like, turn so far into the corner that it looks like they're going to fall over?
Correct. Right. Because the only way, otherwise you're going to rotate. You're going to fall over. You're going to rotate like this. Unless I lean in it enough so that the centripetal force is acting enough up my body that I don't just flip over. Yeah. So we don't have a force that's pushing us out. So it's not you pushing against the door. It's the door pushing against you, and what you feel is just the reaction to it. But you didn't initiate it. You thought you did. You thought you went slamming against the door, but it really wasn't that. It was the door slamming against you as the car turned.
It's all the car's fault.
It's all the car's fault. All right. Centripetal force is simply the name given to the net force on an object in uniform circular motion. Any type of force or combination of forces can provide this. For example, friction between the race car's tires and the circular track is what provides the centripetal force that keeps the car in a circular path. So this becomes more and more important as the road gets wet and you start losing some of the ability of the tires to stick. The coefficient of friction goes down when it gets wet between rubber and concrete, and so it can provide less force. So you're going to spin off that road much more easily. You know that intuitively, but there's the physics words to put with it, the physics reason to put with it. Another example, gravitational force is a centripetal force that keeps the moon in its orbit. Here we are, the Earth. The moon is orbiting around us. What's pulling the moon towards Earth so it goes in a circle? It's gravity. It's a gravitational pull that is keeping it that goes in a circle. So the bottom pictures here are dealing with a vertical twirling circle instead of a horizontal one. First I say, if the centripetal force vanishes, the object stops moving in a circular path, and what path does the object follow?
Straight.
Just a straight line, tangent to the radius, at the point where the force vanished. A ball that is on the end of a string is whirled in a vertical circular path. So here we are in A, we're going in a vertical circular path. And if my string breaks right where I am horizontal, well, that ball will keep going tangentially. It will go straight up. If we are doing a vertical twirl like this, and it breaks right here where the string is straight up, well, that ball wants to move straight this way, but why is it dropping? Gravity. That's obvious. That's easy. What's happening there? So it'll move in a parabolic path along that bottom one because gravity is getting in the way. So let's try problem 228, number 2. And in fact, if you look on 229, there's your picture of the car and the passenger and the path of the car. And they kind of did a bad thing there because they're trying to make the path of the passenger curved. The passenger really wants to go straight. I guess if they stay in the car, they'll curve too because they're in the car. All right, 228, number 2. A bicyclist is riding at a tangential speed of 13.2 meters per second. Now what that means is his odometer on his bicycle is telling that's how fast he's moving forward, 13.2. That's not how fast he's turning the corner, how fast he's moving forward. Turning the corner is an acceleration. The magnitude of the centripetal force is 377 newtons. Centripetal force. The combined mass of the bicycle and the rider is 86.5 kilograms. What is the track's radius? Well, again, if we know the formula, it's pretty straightforward. What is the formula for centripetal force?
That's velocity squared over radius.
mv squared over r.
Whoops, I used the wrong v sub t squared over r. There we go.
V sub t.
Tangential speed velocity. Tangential, that's what the t is talking about. Okay, we're trying to solve for r again, aren't we? Multiply by r, divide by our force. Mass, what do we have, 86.5? We were moving at 13.2, which we'll have to square. 877 newtons.
377.
377 newtons. After you operate your calculators correctly, you get how big a circle? What is the track's radius? Christian?
40.0.
40.0? 40.0 unit
Meters.
meters. Radius is measured in meters, the distance that you travel there. Easy enough. Have you ever been at a state fair and ridden in one of those big circular things
Yep. I love
that spins you around and then they drop the floor out from under you?
I love that.
Oh, I hate that. That is awful. Yes, that is awful. But why are you sticking to the wall? Because of centripetal force. What is centripetal with a P? It's a force directed
Outward.
inward towards the center. The wall of that is pushing on you hard enough, and then you'll have to have some friction. It's pushing on you hard enough that it keeps you stuck to that outside.
Wait, you're not talking about the swings?
No, it's like
Not the swings. It's like you're in a big barrel.
Oh, that.
And you're standing up against the wall, and then they start rotating you, and then they drop the floor out from under you. And if you've been in one of those are awful. Don't go in. But some of you will like them, but anyhow. So that's what's going on. Now, centrifugal, the word with an F, we will, and Nate, probably good for you since you're the one that keeps bringing this up. Centrifugal, the word with an F, will never appear in this physics course. There is not a centrifugal force.
Why do people say so?
Not a centrifugal force. It's the result of inertia. So we use the term centrifugal with an F, usually not in physics, but we use it in this region. Remember when that car is turning and I'm pushing up against the door? Then that's what we call the centrifugal, you pushing up against the door. But it's really not. That's just a reaction to the centripetal force, the force that is pulling you in.
So basically, centripetal force is like the opposite of centripetal force for layman.
It's just correct for laymen. Correct. That's what it is for people who are not the physics people. And we're the physics people. Now, we use that word with an F to describe machines. A centrifuge. What is a centrifuge? Heard the term?
It spins stuff really fast to separate things out.
It spins, and let me take blood for an example, because they'll use a centrifuge on the blood that they draw from you to separate plasma and whatever else they separate when they spin your blood. Because at different masses will experience a different force on them, and so they will separate when you have a screen. So you can separate them because of the different forces that you're applying to it. When you want to test, let's say, military pilots or astronauts, they put them in the big centrifuge. I'm sure you've seen the picture. A big arm in this room, circular room, and they start winding that thing up. And you can use the centripetal force to figure out how much of a force that person can withstand before they black out. And there are techniques that you can use to try to keep your blood in your brain. They essentially are squeezing their muscles, their core muscles, as much as possible in order to keep the blood from draining away. And that's what a G-suit does. It just has air that is squeezing your feet and your legs and your body, trying to keep the blood up to your head when you do those high G turns, high acceleration due to gravity, high G turns, so that the blood doesn't go away from your brain, and when the blood goes away from your brain, you just black out. So that's not good when you're flying the airplane. No, correct. It can't be indefinite. So you can pull that tight turn and survive through it for 3 or 4 or 5 seconds, and you need to release so that. So no, you just can't keep pulling it, because at some point you're going to black out. Describing a rotating system. What's different between rotating and circular?
It's moving itself.
The object itself is rotating, like a CD, a DVD, a turntable, a microwave table. Rotating. There you go. Those are things that are rotating. To better understand motion of a rotating system, consider car. Oh, did they use the wrong thing? They used the wrong word. As the driver makes sharp left turn, the passenger slides to the right of the door. We've already talked about this. The car is circular motion. They used the wrong word.
Yeah, it's in my book. That someone crossed over too, so he wants to say
Yeah, this is circular. This is circular motion that they're describing right over here. The car enters the ramp. Oh, I think we already talked about this. Travels along the curved path. The passenger, because of inertia, Newton's first law, tend to move along the original straight path. If a sufficiently large centripetal force acts on the passenger, maybe it's the seatbelt, maybe it's the side of the door, Maybe it's the friction between your corduroy pants and the velour seats in your car. I don't know. The person will move along the same curved path the car does. The origin of the centripetal force is the force of friction between the passenger and the car seat, or the seat belt, the door, whatever it is. If this frictional force is not sufficient, the passenger slides across the seat as the car turns underneath them. And if the door is open, they go right out the door. So let's study a little bit more about gravitational force. Orbiting objects. Orbiting objects are moving in circular motion. So orbiting objects fit into this chapter. And yet they say here, now wait a minute, free fall. Now I've already talked a little bit about this. How is an orbiting object in free fall?
There's nothing touching it.
Let's look at this diagram and we'll clarify it a little bit. Here we have this cannon on the mountaintop. And they shoot their cannonball. Now not very fast, so it just goes out and drops down because gravity is pulling it towards the center of the Earth. If I shoot it faster, well, it will go farther before it splashes down. If I shoot it fast enough, gravity continues to pull it towards the center, but it is moving fast enough that it just keeps moving in a circular path, falling all the way around the Earth and continuing to fall all around the Earth. Nate?
So whenever ever, like, is it coming closer to the planet, or is it just
Not at the proper speed. Orbital speed, it's called. There's an orbital speed, a tangential velocity, that is just right for every radius from the center of the Earth, for every orbit level. So there is a correct speed, and since we're in space, it's not going to slow down, but it really does a little, because space is not totally void of any matter out there.
Yeah, shoot that cannonball fast enough to come around and hit the cannon.
That is what has happened. Now, in real life, a cannonball is never going to be able to be shot fast enough, but correct. That is exactly what would happen. It would orbit the Earth and come around and hit it. Now, let me correct that just a little bit. You're still in the Earth's atmosphere here, and so the friction with Earth's atmosphere, it would slow down and fall. So you would have to get this cannon up into space, and then you shoot it, and then it'll come around and hit you.
So what I'm saying is potentially that if you went into space and you
Yes.
calculated the distance from you to the center of the Earth, you could
Yes.
use your optical count, like,
You would know your orbital speed.
okay,
It
so
wouldn't actually come around and hit you, though. It wouldn't be able to come around and hit you, because how would you be up there unless you were also in orbit? And if you shot it fast enough,
You're on a really, really tall tower.
backwards.
You're a really, really tall tower.
Pretty sure that tower.
if you're the same mass as the cannonball, you launch a rocket, the rocket just like stalls right here, boom!
Yeah.
Two things in orbit.
Yeah, and then you're gonna hit it.
There are a lot of interesting hypothetical things, yes. But these hypothetical things, by the way, that you're talking about, are amazingly the ideas that begin to be turned into technology. They are, theoretically, they are studying, can we launch things into orbit by literally building a tall tower? It is possible, theoretically, to actually build a tower that reaches clear up into space. And that will, with the current technology, it's theoretically possible. It's hard for me to believe, but I have read that is true from reputable magazines.
Well, that's a good idea.
So I don't
I've
know.
tried that before. We ended up like 15
You
years
would get hit by
Yeah.
like asteroids and meteorites, so.
There is a problem with space, yes.
The breathing part?
All right. Centripetal force that holds the planets in orbit is the same force that pulls an apple towards the ground, gravitational force. Gravitational force, mutual attraction of force between particles of matter. We already, I believe, have talked about, anytime I have mass, there's a gravitational attraction between those masses. So if we have these planets, there are gravitational forces between them. Newton, hey, that guy again, developed the following equation that describes quantitatively, so you get the numbers, the magnitude of the gravitational force if the distance r separates mass 1 and mass 2. So this really works for any two masses. It doesn't just have to be like the Earth and the Moon. It works for any two masses. Newton's law of universal gravitation. Gravitational force, force due to gravity, equals Now here's this big capital G. It's called the Universal Gravitational Constant. There's the number. You'll use it enough that you'll probably memorize it. 6.673 times 10 to the negative 11. And then a whole bunch of units. Always that number, we believe. Universal, should work anywhere in the universe, we think. Gravitational constant, remains the same. Now where this came from was from experiments. Look in your book to page 235. Look at 235. Here is Henry Cavendish. He used this experiments to determine the value of that big G, universal gravitational constant. He has this unwound string. It has to be string or a thread that is not twisted. I should have said untwisted. This is twisted. So if I let this go, it's going to start rotating because it's twisted string. So you have to have something that is not twisted fiber, an untwisted fiber. So if you let it hang there, it has no torque itself. It will not twist anything by itself. He has a mirror there. He has this rod with two little masses on it. And then he put it between two larger masses. And when he shone a light on that mirror, very slight changes, movement, the attraction, gravitational attraction between those masses would then move the mirror just slightly. And he would see the light reflected at a different spot. So he could have a fairly fine instrument, high precision instrument, just from those very simple things right there. And he did it with different masses, calculated how much it turned and how much force it would take to twist that string. And he was the one that calculated this G, this number right here. I don't know how long it took him. So maybe it's his PhD project or something. I don't know. It was a long time ago. So here you go. Here's our third formula that we have for today. Gravitational force, universal gravitational constant, times mass 1 times mass 2 divided by the distance between them squared. We call it R for radius because if they're orbiting, then it would be the radius. The distance am to an object that is orbiting would be a radius distance. So that's why we use R for the distance instead of D.
Sir Isaac Newton realized that the force of gravity makes a small object, like an apple, fall toward Earth because Earth and the object are attracted to one another. Only the apple appears to move, however, because Earth has so much more mass. In Newton's law of universal gravitation, he explained that all objects in the universe attract each other through gravitational force. The mass of the objects and the distance between them affects the size of the force. Newton's law states that the force of gravity depends on the product of the masses of the objects divided by the square of the distance between them. In other words, if two objects are moved twice as far apart, the gravitational attraction between them will decrease by a factor of 2 times 2, which equals 4. So, the gravitational attraction between two objects moved twice as far apart will be 4 times less.
Or 1/4 as much. Whichever way you prefer to think of it or look at it. 232, number 2. Mars has a mass of about 6.4 times 10 to the 23rd kilograms. Mass of Mars. Wonder how they got that mass. Did you ever think of that? It's a big scale. And Moon Phobos has a mass of about 9.6 times 10 to the 15. So mass of Phobos. 9.6 times 10 to the 15. Yeah. We're going to see if we can answer that question. That's very interesting. How in the world did they get that? If the magnitude of the gravitational force between the two bodies is 4.6 times 10 to the 15 newtons,
The radius?
gravitational force between them, 4.6 times 10 to the 15 newtons. How far apart are Mars and Phobos? They want another radius. F sub g, gravitational force equals, what's the formula?
Constant.
Gravitational constant?
M1 times M2.
Over R squared.
There you go. That's it. So again, we're trying to solve for r. So multiply by my r squared, divide by f of g. We'll get to the r in a minute. Or how do I get to the r instead of r squared?
Take square root.
Square root.
So R is only squared in this one.
Wait, so G goes on top now?
If I have a number by itself, not written in a fraction, where is that number? Numerator or denominator?
Okay, yeah.
It's numerator. It's in the numerator. I mean, I could put it in front. Doesn't matter. I think they gave us some numbers. 6.673 times 10 to the negative 11. Need some more space than that, I think. These numbers are kind of big. Mass of one object, 6.4 times 10 to the 23rd. And 9.6 times 10 to the 15th. And if we divide that by 4.6 times 10 to the 15th. This would be a good one for all of you to try because it has all these scientific notation numbers. To make sure that you're able to enter your scientific notation numbers well into your calculator and get a correct answer. So remember there's a scientific notation button, 6.673. Often it's just that button that says EE. And then I do negative 11.
So if I did this in scientific mode, it would do the same thing with it.
You still have to enter the number. It's going to be a big radius. I mean, they're not just hands width apart.
8.91 E43.
No. Oh, I'm not writing it yet.
Okay, I got
944,666.
9.4 times 10 to the 6th. I was going to say, can you write it in scientific notation, the correct number of significant figures for me? 9.4 times 10 to the 6th. That's the right number. What? Meters. So, is that right? No, that's right. 9 million meters, or it would be 900,000 kilometers. So that maybe gives you a little scale. 900,000 kilometers. They're a long ways apart. So how, let me see if that's next. How do we get things like, and let me use the Earth. How do we get the mass of the Earth? Obviously, we don't set it on a scale. I think you know that. How do we get the mass of the Earth?
Take the circumference.
Well, let's look at this formula. Force due to gravity. And this was all done without having to try to weigh the Earth. We looked at Cavendish's experiment there. Let's look at this formula for a minute. And let's say that one of these things is the mass of the Earth. So I'm going to call that E, mass of the Earth. And I'm going to say this is the mass of some object. Maybe it's my pair of glasses. I know another way of determining the force due to gravity that is acting on these glasses. How can I get the force due to gravity that's acting on these glasses?
the weight.
Which is called weight.
Yeah, the mass.
It's the mass
Times 9.81.
times the acceleration due to gravity, 9.81. So I could take the mass of my object multiply it times the acceleration due to gravity, and that is supposed to equal this thing. And in fact, I don't even need the mass of the object. They're gone. Let's see if we can isolate the mass of the Earth there. Mass of the Earth, well, I'd have to multiply by the radius squared over here, g(r) squared, divide by universal gravitational constant, which we experimentally found. Did that do it? How do I get the radius of the Earth?
Somebody has it.
Well, we're going to look it up, but actually it's not too hard to do. I have a little video. Maybe I should show you guys that video. I have a little video of how they did it originally. And it's, you work with some shadows in two cities that you know how far apart they are, and they need to be quite a ways apart, or two locations quite a ways apart. You can figure out what the radius of the Earth is. But let's use the number that we know that we can look up. Well, we know gravity, 9.81. The radius of the Earth, why don't you look in the back of the book, I think inside the back cover, they have some constants back there.
Yeah.
Left side, maybe, somewhere.
6.38 times 10 to the 6 meters.
What?
Mass, radius of the Earth, yeah, 6.38 times 10 to the 6, is that right?
Yeah.
Now that has to be squared, and now we need to divide it by 6.673 times 10 to the negative 11. Try that, now that you're experts at scientific notation. And I can help you later if you're not experts yet on your calculator of energy and scientific notation.
Seems like a little bit. I don't know why it seems like a small.
9.379 times 10 to the 17.
Anybody else getting that?
5.98 times 10 to the 20.
I like that number.
Negative.
5.98 times 10 to the, what did you say?
24th?
Yep.
Now I want you to look right beside probably the radius of the Earth in your book, and what did I say the mass of the Earth is?
5.97 times 10.
There you go. There you go. So we don't have to put the Earth on a scale. We can figure out the mass of the Earth other ways. We'll see if we have time to look at that other video. The gravitational forces that two masses exert on each other are always equal in magnitude, opposite in direction. Newton's which law?
Oh, second. Third.
Third law, the equal and opposite. This is an example of Newton's third law of motion. I didn't even notice that when I asked the question. One example is the Earth-Moon system shown right here. As a result of these forces, the Moon and Earth each orbit the center of mass of the Earth-Moon system. So when the Moon is going around the Earth, it has an effect. The Moon has an effect on the Earth, not just the Earth on the Moon. So the center of that is actually the center of mass. The center of mass. Now I believe the center of mass is something like that. It's still within the Earth, because the Earth is so much more massive than the Moon is. What's the Moon? Do they have it there in your book?
They have Mars and Pluto.
Oh, they don't have the Moon? Our Moon? Okay.
But it's smaller than 1.25.
Oh, look at that. This center of mass lies within the Earth. Sure enough. That was a true statement. That's always good.
Mr. Bishop,
Yes.
do you weigh less if the moon is overhead than if you do if it's underneath you?
Oh, there's a good physics question. So, the Moon. Let's say it's right overhead. Now it's... now I guess you could get to the right spot on the Earth. It's right overhead. Are you going to weigh less?
Doesn't it just cancel out?
Yes, because you have the force of the Moon pulling up on you while the Earth is pulling down on you, so you'd have to combine those two forces to get the net force, which is your weight. So yes, not significantly different, yes. But what does, there's a very significant difference that happens because of the pull of the Moon, deals with water. What does the Moon? Tides. It's the pull of the Moon that is creating those tides. The biggest part is the pull of the Moon. There are other things involved in it. But the Moon is the biggest factor in our tides. And it's dealing with the position of where the Moon is. All right. Where are we
Says it
here?
right there, high tides.
Oh, look at that. Newton's law of gravitation accounts for ocean tides. High and low tides are partly due to the gravitational force exerted on the Earth by the moon. I want to try to look at that video too. We probably won't be able to see them all. The tides result from the difference between the gravitational force of the Earth's surface and at the Earth's center. Cavendish applied Newton's law of universal gravitation to find the value of g in the Earth's mass. We looked at that. Two masses, distance between them, gravitational force are known. Newton's law of universal gravitation can be used to find g. Once the value of g is known, the law can be used to find Earth's mass. And that's what we did. We found Earth's mass. Now, gravity is a field force. What does that mean?
It's not.
Oh, it's not
contact.
force.
Don't need contact. Don't need contact. So as long as I am within gravitational field, which is just mean any location where you feel that force, you're within the field. Gravitational field strength G, the strength of the gravitational field is the same thing as the force of gravity divided by mass. Now earlier, we used this just a second ago. We used force due to gravity, or weight, is mass times acceleration due to gravity. But these are actually two different ways of calculating this g. They use the same g because it's the same value. The gravitational field g, the strength of the gravitational field here, these little arrows, as I'm closer to the Earth, it's stronger, is a vector with magnitude g, points in the direction of force due to gravity, center of the Earth. The gravitational field strength equals free fall acceleration. They're actually two different concepts. The strength of the gravitational field and the acceleration due to gravity are two different concepts, but they are exactly equal to each other in magnitude and number. They both are 9.81, the three significant figures. Weight, we've already learned this, is mass times the gravitational field strength. We just did it gravitational acceleration due to gravity before, but it's the same thing, gravitational field strength. The number is the same. Because it depends on the gravitational field strength, weight changes with location. Yeah, we knew that. So weight is mass times gravitational field strength, or acceleration due to gravity, the little g there. So if I wanted to find, let's look at this progression here. If I wanted to find a formula that tells me how strong gravity is at different locations, well, they have just started with that weight formula. Force due to gravity is m times g. They rearranged to solve for g. And then this is the force of gravity formula right there. Mass 1 times mass 2. It's just mass 1 is your object. Mass 2 is the Earth in this case. Divided by the radius squared. Well, if I just multiplied it by that mass on the bottom, I get this thing. Those masses cancel, and I get this equation. So this equation will tell me the gravitational field strength, or the acceleration due to gravity, on any planet or object. Universal gravitational constant times the mass of that object, or mass of that planet. If it's Earth, we put Earth there, divided by the radius of that object, in this case it's Earth, squared. On the surface of any planet, this formula, the value of g as well as your weight will depend on the planet's mass and radius. Look in your book to page 236 for a moment. There's a little purple box in the column, the left-hand column on page 236, Conceptual Challenge. See how well you do with this concept. A couple of concepts here. Gravity on the moon. The magnitude of g on the moon's surface is about 1/6 of the value of g on Earth's surface. Can you infer from this relationship that the moon's mass is 1/6 of Earth's mass? Why or why not? So they say g on the moon is 1/6 of g on the Earth, little g. Can we say that Earth must be 1/6 as massive as The moon is 1/6 as massive as the Earth. What do you think?
Or because it's the distance away from the center too.
No, because it also involves the distance you are away from the center of that object. So it's not only mass that affects it. So the moon's mass is less, but so is the radius of the moon. It also is less. So the moon is not 1/6 the mass of the Earth. It's more than 1/6 because we're also reducing the distance there. Very good. So you passed conceptual challenge number 1. Look at number 2, selling gold. Listen to this one. You think you guys have far-fetched ideas? Scam artist. Scam artist hopes to make a profit by buying and selling gold at different altitudes for the same price per weight. Should the scam artist buy or sell at the higher altitude?
Should buy it.
Buy higher altitude, sell lower.
Absolutely. Because as I move farther away from the center of the Earth, this R gets bigger, and therefore the weight of that gets less, smaller, less. If you want to lose weight, all you need to do is get in something and go to a higher altitude. You've lost weight. If you run up there, you can lose a lot more weight. But anyway, so he should buy high, right? Buy high takes on a new meaning. Buy at a high altitude. And then comes down to sea level and sells it. Would that be true?
Whoa.
He's paying the same price per ounce. So up here, there are fewer ounces. Down here, more ounces. Makes money, right? What do you think?
Well, I mean,
Yeah,
Is that a new
Yeah,
scam?
It would be so insignificant, you made like $5.
The problem is you're even going to lose money because it's insignificant enough, it's different, but it's insignificant enough that by the time you pay for transporting that gold from the top of the mountain down to sea level, you've way blown your money. So it's true,
But
you
not
buy it up here,
practical.
but not practical. It's not going to work out.
I could sell that.
There's a sun guy with a little box of gold.
So much for that scam, which is probably good anyway. All right, let's see here. Oh, wow. Turn in your book back to page 233 for a moment. Black holes. Brief description. When we talked about orbital velocity, there is a velocity that I will orbit around my object. Depending on how far away I am, there is a certain speed, a certain velocity while I will orbit around that object. If I am going faster than that, let's say I'm flying along through space and here's this planet. If I am going faster than that, gravity will affect me, but I'll just turn and head off in another direction. So that happens with meteors and comets all the time. They're affected as they're flying through space by gravity of different objects. If I am going slower than this speed and I come in here, I will crash. Now, this is what happens with satellites. They have an original orbital velocity that is just right, keeps them going. Most of them will have some booster rockets on them because there's friction up there. There's stuff in space. It's not purely a vacuum. So there is some friction. So over time, years, they slowly lose speed, and they slowly then lose altitude. And if they lose enough altitude, they've crashed into the, hopefully, ocean instead of the ground. So they'll have booster rockets to help maintain their orbital velocity, but at some point they run out of fuel. And so all the time, now doesn't mean it happens every week, but periodically you have satellites that crash down to Earth.
There's like a site where you can go and look at everything and see like when they're going to fall.
Yeah, there you go. You can look online and you can find a place and and it's based on, hey, they're losing enough speed and they're going to crash right down here. Light has mass. So we'll talk about that later on. But light has mass. Light itself has mass. And so it is affected by gravity. Now, light has a constant speed, 3.00 times 10 to the 8th meters per second. So, if I have this massive object right here, really massive object, And that object is really, really dense. So it doesn't even have to be big. It just has to be very, very massive here. Well, the more massive I am, the more gravitational pull I have. And at some point, I can have a strong enough gravitational pull that this massive object will affect light exactly like I drew right here. When light was fast enough, it would be bent by that object as it gets massive enough to have a strong enough gravitational pull. In fact, that is how they find often planets. They see light coming and they know it has been bent. They can't see the planet out there, these new planets that they're discovering, they can't see the planet. But they can see that light is being bent.
See the white beams?
And so, I don't know what they use to get the direction of it, but that's what they're using. They know that light has been bent as it comes around, so they know there's an object there. Yeah.
So basically, they see something. So, like, if you were looking in your telescope, theoretically, you could see a thing out in space, and it could totally not even be there at all. And that's not just based off of the amount of time it took to reach you.
Correct, because it's here, and that light that came from it was bent. You think it's out there.
Wait a minute. What if
It's over
there
here.
was something beside, like you're here, black hole's here, and it's here. You can see the light straight from it, but at the same time, you can also see the light that went around it. So do you see two copies of it?
No.
Oh.
Let's finish up this bit about black holes, a theory of black holes at least. So we have some radius right here where this light is close enough that it is at this point at orbital velocity. So that light will just circle right here. You will not see it because the only time you can see it is when light gets to you. So you can see this, but you can't see the one that's orbiting there. This is called the event horizon. And the reason it's called the event horizon is because anything closer than that radius right here never comes out. That light just goes in. Nothing can come out. Light's the fastest thing we know in the universe. It moves at a constant speed. And so if no light comes out, then what do I see? The absence of light, which we call black. The absence of light.
So
That's the idea on a black hole. Question over here and then this.
So a black hole isn't even a thing. It's like just you can't see it. So at the center of that black hole is what's actually there.
Yes, there you go. The center of a black hole, we believe. We can get no information out of this, though. The only way you can get information is if something comes from there to you. It's the only way you can get information. And nothing, our theories here, this is the idea of what a black hole is, nothing can come out because the gravitational pull is so strong it lets nothing out. Light is the fastest thing and it doesn't even let light out. So nothing comes out. So we believe that the reason we see these black regions, these black holes in space, is because there's a very massive, dense object in there that is creating this super strong gravitational pull that's sucking everything into it that is within its reach. Ben, you had a question.
So, like, you can't see them if you look at them?
You see black, which is the absence of light.
You don't even see a black object, you just see black.
Yeah, you just, like...
Correct. Now, when we see black, I mean, you look at the table cloth, you see this black, because it's not really pure black. There's light that reflects off of it and comes to you. But you have been in a cave where it was black enough that you couldn't see your hand. I mean, that's a black hole. I mean, there's nothing, no information comes.
So, like, you wouldn't be able to tell if it was, like, right there? Like, if it was close to our galaxy?
You would see the black.
You would? So
Yeah, you'd see the absence of light. You would see light around it.
Yeah.
Stars around it. Nothing there. Nothing there is what you would see. Nothing.
But there could be stuff in it.
Absolutely. We believe there's stuff in there.
Oh,
Where does it go?
That makes so much more sense.
We believe there's stuff in there, but we can't see it. So on 233, you can read a little more about it. We think if you have a massive star, and I'm not into astronomy, I don't know all the names of them, but if they burn out and collapse, then you form a very high dense, massive object that can form a black hole. That's the theory. Now, any theory is a theory, cannot be proved. And I found this very interesting that I ran across a couple of years ago. It probably had, maybe it even has the date on it. Oh, no, this is today's date. So anyhow, black holes do not exist. Big Bang Theory is wrong, claim scientists, and they have the mass to prove it. In other words, the formulas, everything in physics and science is based upon formulas. We've discovered that. So right here is just a little synopsis about one of the, I don't want that video, whatever it is. Biggest unanswered question about black holes is the so-called information paradox. Under current theories for black holes, it is thought that nothing can escape from the event horizon around a black hole, not even light itself. Inside the black hole is thought to be a singularity. That's one little spot that's extremely massive, singularity, where matter is crushed to an infinitesimally small point as predicted by Einstein's theory of gravity. However, a fundamental law of quantum theory states that no information from the universe can ever disappear. So this creates a paradox. If you have a black hole, anything in it has disappeared, cannot be found again. But this other ideas that we have say, and experimentally there's evidence that back those up too, say information can't disappear. So you have a paradox. Something's not right. Something's not right. We don't know what that something is. Is the theory on the black hole wrong? Something's not right. So there are some contradictions that go on with it. I want to show you about tides just a little bit. But read about the black holes on 233. It's just a page there. It's really interesting. So here comes a little video of how tides work. And see if you can follow it. He gets fairly detailed, but fairly straightforward. Oh.
I'd like to watch it from the beginning.
Let's start it from the beginning.
For centuries, people have wondered about the role of the moon on ocean tides. Here's the moon in empty space. Not quite so empty, for in its vicinity, let's suppose there's a giant blob of water. For the moment, we'll assume both are at rest. If no external forces act on the giant blob, it's pulled inward by both surface tension and its own gravity to take the shape of a sphere, the shape having the least surface area. But there are external forces on the water. The moon exerts gravitational forces on the blob and forces that are not uniform.
It's bigger, closer.
Since the force of gravity between two bodies varies as the inverse square of their separation distance, the moon pulls harder on the parts of water closer to the moon than parts farther away. If the body of water is closer to the moon, the elongation is more pronounced. Not only are the forces greater, more importantly, the difference in forces between the closest and farthest parts is greater. Opposite sides of the blob seem to be stretched apart. Let's move the water back a bit and put planet Earth in the middle of it. And let the planet spin, say, one rotation each day, looking down at the North Pole and watching Earth rotate, and observe at the seashore.
Notice it's elongated.
The water is deep here. Hey, high tide. Oh, notice the water is becoming less deep. And here we're at low tide, the best time to dig clams at the beach. Then the water begins deepening again, and before you know it, we have another high tide. The cycle continues. This computer animation makes this clearer. Nearer the moon, we see a greater stretch. Put a solid body inside the blob, move it out a bit, and here we see a North Pole view of Earth rotating daily beneath the ocean bulges. So with each rotation of Earth, we get 2 high tides and 2 low tides. So we see how Earth is elongated by the difference in lunar poles on it. The elongation is on opposite sides of Earth, so it doesn't make sense to think that the elongation is only on the side of Earth that faces the moon. A corresponding elongation occurs on the moon as well, even though it's solid. Consider the elongated moon, as I'm drawing, very much exaggerated to help me explain an age-old question. Why does only one side of the moon face us? The moon, like all bodies that rotate, rotates about its center of mass, shown by this purple dot. Here's a situation where the center of mass and center of gravity don't coincide. Because one side of the moon is closer to the Earth than the other, The close side is more gravitationally tugged toward Earth than the farther away side. This results in Moon's center of gravity being somewhat closer to Earth than its center of mass. I draw this with the red dot.
Let me pause it right there for just a second to understand what he said. Center of mass is going to be the center of the object, the mass. Center of gravity is where the center of all the gravitational forces are. And because the moon is longer down here, bulging, exaggerated, that center of gravity is going to be closer to the Earth. Now he's drawn it at an angle for a reason to explain why the Earth keeps facing the same direction to us all the time.
And a purple dot for Earth's center of mass. This red vector from the moon's center of gravity is the gravitational force that Earth exerts on the moon. The moon's long axis through both its centers of mass and gravity is shown by this white dashed line. The result is a torque above the moon's center of mass, which tends to rotate the long axis of the moon into alignment with Earth's gravitational field. We see the same behavior with a compass needle that aligns with a magnetic field. Once aligned, the torque no longer exists. The alignment of Moon's long axis continues as the Moon circles Earth. We say the Moon is tidal locked to Earth. How about that? Now, getting back to ocean tides. It so happens that the Sun also plays a role in ocean tides. Because of its vast distance from Earth, the difference in its poles on near and far sides of Earth are much less than Moon's difference in poles. Although less than half as effective as the Moon in raising tides, Sun's influence is there because it's so massive. Most noticed when the Sun, Moon, and Earth are aligned. Here we see the Moon in its new Moon position. Tidal influences of Sun and Moon coincide when this alignment occurs, producing extra high tides and 6 hours later, extra low tides. At times when the alignment is perfect, so the Moon casts a shadow on Earth, we have a solar eclipse. But that's another story. These greater than average tides are called spring tides, although they have nothing to do with the spring season. Spring tides occur at or near the time of a new or a full moon. When the Moon is not in line with the Sun, when it's positioned 90 degrees to the line between Sun and Earth, tides due to the Moon and Sun partly cancel each other. That occurs when an observer on Earth sees a half moon in the sky. How do you think tides are affected at this time of month? Did you say smaller high and low tides then? If so, you're correct. These tides are called neap tides. Our treatment of tides is simplified. Average high tides are only a meter or so above the average surface of the ocean. So the bulges we depict are greatly exaggerated. And why the tidal bulges don't line exactly with the Moon or Sun, why they don't occur at the same time each day, and why variations in tides occur in different parts of the world, these all make up another story.
There's a little bit about tides. And if you look in your book, where's your tide picture? Page 234. Depending on the shape of a bay or an inlet of the ocean, you can get very dramatic changes in water levels or tides. Bay of Fundy in Canada has tremendous difference. It's like meters different between a high and a low tide as the water comes in and gets funneled in by that bay. All right, that's sections 1 and 2. Homework from sections 1 and 2.